fine. Okay.
All right, thanks everyone for joining this kind of special joint meeting between the UNLV's Star and Planet Formation Group and PFIT's collaboration. So today I'd like to introduce Alex Ziampras. He got his PhD at Tübingen and did his first postdoc at Queen Mary University in London. And now he's a postdoc at LMU Munich. And today he's going to talk about some interesting simulations on irradiated protoplanetary disks. So go ahead, take it away, Alex.
Thanks for the introduction. It's great to have everyone here. Thank you all for inviting me, actually. I would like to keep this as informal as possible. So I was told I have an hour to talk. I'm not going to take the full hour. So please feel free to interrupt with questions or comments, or if anything looks unusual, please let me know. So yeah, the topic is shadow disks in general and the dynamics. And the motivation is that we've seen about a dozen of these, at least about a dozen of these kind of disks in scattered light. You can see on the right, there's all these observations where there's dark lanes in scattered light. Unfortunately, I can't point on with my laptop. I can just describe it. But you can see these dark lanes on the 3 out of 4 of these panels, and on the bottom right, you see a wide shadow covering the left half of the whole system. And so not only that, but you can sometimes maybe correlate some of these, the observation of these dark lanes with additional structures, such as these spiral arms that you see there on the 2 left pictures, as well as these arcs that you see on the bottom right. So then there's some argument to be made about whether are these two related, what's driving these, what could be the cause of this substructure.
Oh, I see that. Yeah. Can people see? Can people see his pointer now? Do you see a cursor on the screen?
I do not.
No.
What if you use the green pencil or something? Use it.
That's
Try that.
with the drawing, so I don't think they can see the drawing.
Well, try clicking. Can someone see if he draws?
They can see a dot.
That might not.
But then
What's a green one? Green one.
I think green runs the color.
Yeah, I think it should be the mouse. Oh, but because I don't see your screen, they see my screen. That's why they don't.
On your end, if you do annotation.
Oh, right. Let me try to go there. And yeah, don't even have the cursor here.
I see.
Click. No, still don't see the cursor.
Okay. Oh, that's okay.
Yeah, and they don't see the cursor because it's on your screen.
Yeah. Okay.
It's fine. That's a revolution. So let me.
Or if you want to point for the people in person, you could do that too.
I can do that. Sure. Yeah, I can do that for the people here at least. But I can still do my best to describe these things for people online. Right. So as I mentioned, the main question is what's the cause that drives these spiral-related features, and how would they evolve in time? So you can imagine if you take a typical passively radiated heated disk, then it would look something like this. So you have a star in the center, then you have a flared structure around the star. And now if one common way to cause these kind of structures is to have misaligned inner components. So if I were to now tilt the inner part of this by some angle, you can see now that along the line that connects these two disks, along this axis that the inner component has been rotated against, you can see these two dark lanes, right? And that's the idea here. That would be causing these observations of scattered light. So you would see these regions on top and bottom as darker. And of course, this depends on the angle of the misalignment. So if it's less misaligned, you will see a wider shadow on the surface, and you can even cover half of the disk with just a misaligned component in the center.
Alex, how did you make this?
I made this on Keynote.
Oh,
I'm
Keynote.
saying that I love this software.
Yeah, hard.
So this is literally the 2 different disks that I then zoom one in, and then I put it inside. You can twist it at any angle you want. It's kind of cute. But yeah, Keynote is kind of in between. I'm not sponsored by Apple, right? edging the gap between presentations and software design. No, I mean graphic design. Yeah, so that's the idea, that if you have misaligned in a component, depending on the misalignment angle, you can have a different degree of or a different width of shadows on the disk surface. You can cover basically from narrow lanes to half the disk. And of course, you can play this game for multiple misalignments. So there's actually a particular observation of this HD 139614 system, where you can see on the top left, on the top right, that more than half of the disk, of this left side, is actually covered by a shadow. So this implies that maybe there's more than one misaligned components in the inner disk. And the best fit model, by just geometrical arguments, by just adding misalignments until you get it right, is by having two misaligned components, where you can see on the bottom left, you have your star, and there's the component 1 that's casting a shadow on half the disk, and there's component 2 in between, like a misaligned ring that is extending that shadow further, but it's also itself partially shadowed. So then if you combine these two and now you do a synthetic observation, you arrive at the picture on the bottom right. So you can argue that simply by geometrical arguments, you could get spiral, you could get these arcs, you can get these blob-looking things on the far inside, and so on. But that's not the end of it, because even if the inner component is very weakly misaligned, then that means that still along the two lines that connect, along the axis connected to disks, there's going to be a shadow that hits the midplane. So even though there's going to be a shadow hitting the disk surface that would be quite wide, it's going to be a darker lane that still shadows the midplane completely. And that midplane now, in principle, should be a little bit cooler than you expect it to be. And yeah.
So there's a question in the chat when you ever read. Yeah.
Unfortunately, I can't open the chat because I don't see my cursor.
Yeah, I can just say, I'm just curious, it was in the observations and also in your keynote, but it's sort of like the lines here, right there. It's not 180 degrees, right? Sometimes it's less, sometimes it's more. I don't know if you want to comment on that. Obviously, that geometry is pretty interesting.
You mean the geometry of this particular system?
So sure, that's one example. Yeah. So there it's like, yeah, it looks like the bright region is less than 180 degrees and the shadowed region is more. And there's
Exactly.
it was just two lanes, and the two lanes aren't necessarily 100 degrees apart. They looked like they were at different angles as well.
Yes. So if you have a weakly misaligned inner component, as you can see from this sketch here, you can get up to half the disk being shadowed. To get more than half the disk shadowed, you need essentially multiple misalignments. So this picture is only possible if you have at least two misaligned components, such that the intermediate ring in between can be up to halfway shadowed, but the outer disk can be shadowed by more than half of its total azimuth. So it's only possible to have more than one misalignment.
Okay, interesting. Yeah, thanks.
And you can start now playing this game, actually, that you can make some connections to warps, maybe, like warps are small misalignments, and a lot of small misalignments in a row kind of act like warps. So maybe you can play this game for warp disks as well. Screw has a question.
A question about the geometries. So I see that you're showing here, first you were showing one misalignment, now you're showing two.
Right.
Then my question is, how discrete are these kind of secondary disks, inner disks, how discrete they are? Are they like a sharp cut, or you would have a sort of like a continuum structure?
I think it kind of depends on your disk parameters. This is simply a model done by Murarena here that is just taking a disk and just cutting it and rotating it at arbitrary angles until you get the best fit. Yeah. So it's basically a discontinuous set of rings of disks in there. In principle, I mean, I don't think there's any process in nature that is discontinuous like that. So these must connect over some length scale, especially if you have some turbulence in between. But you can show that disks that are subject to an inclined forcing, for example, can just break at some points. Now these breaks can realign over time, so there's going to be again a smooth transition between the breaks. But if you have, for example, a disk with absolutely no turbulence, or like a really low turbulence, you could have an almost discontinuous set of disk segments inside.
And then, so a secondary question, then if it's like a sharp cut, how does the radial velocity of material work in this? Like, for example, how does gas would radially move inwards if you have a cut piece? Like, I don't know.
So assuming a radial inward motion due to, let's say, viscous evolution. Yeah, if you have significant viscosity, these will start realigning. So there's gonna be a stress just because the disks are misaligned that will start realigning the disks. So there's actually whole papers on how warps, how motion propagates through warps. And you can see the gas would basically just follow closely to the midplane of its respective disk, but there's going to be also some vertical forces that act in there. That's not something I haven't looked at too much because I'm not going to model the misaligned components themselves. But I think Shangja has an upcoming paper on warps and the 3D dynamics, but there's a lot of people are working on this.
Are those spirals or they are gaps?
No, this idea is that these are not spirals; they're just geometrical effects. By you see part of the
No, I
misalignment.
mean, in the observation, there were like a ring.
Right. Yeah. Yeah. We don't know.
But the model seems to reproduce those rings.
Yeah, it seems to reproduce parts of the observation quite well, just by arguing there's enough misaligned segments. But the question is, if you wait long enough for these to move, will they stay there or will they act as spirals and just move? So that we don't know because these are quite large distances.
Hey, Alex.
Yeah.
So if you have, let's say, one part of the disk, an annulus, right, is kind of tilted, then whichever part is facing the sun or the star will be brighter, right?
Yes.
And that should come up in the scattered light emission. So I was wondering, you see this bright semicircular regions, right?
Yeah.
And that, I mean, can it be like you have actually 3 annulus with 3 different angles of misalignment? So some part of that annulus is actually getting more scattered light emission?
Yeah, that's the idea, that each misaligned component is partially lit, and therefore you see only part of it, like a crescent instead of a ring. And so here they just added enough components, and then you recover all the structures. It's kind of a backward model in a way, from starting from the observation, trying to like fit it with enough misaligned components.
So you are basically having like 3 annulus being misaligned in the inner disk. In this
you
model.
have two tilted components and one not tilted component. Like one, like you have one reference plane and then 2 additional components that are misaligned with the plane.
Okay.
So 3 surfaces to light up.
Okay, thanks.
Yeah. So yeah, as I was talking earlier, there's gonna be a set of 2 sharp shadows that actually hit this midplane, and that midplane then must cool down. And that becomes important from the perspective of dynamics, because most of the gas is in the midplane. First of all, it's like about a scale height above the midplane. And if you now follow that gas along azimuth, that gas is partially pressure supported from the heating coming from the central star. So that means that gas in the hot regions, so the starlit regions on the left, for example, is moving slower than gas moving, rotating inside the shadow region. So if I now show let's say, the radial pressure gradient in the hot or cold regions, it will look maybe something like this. And so if the gas comes in from the left, then you can see on the left here now a graph of the temperature variations along azimuth, and maybe it's not very easy to see on the screen, but there's a band in the center that marks the shadow edges, and you can see the temperature drop as you enter the shadow. The gas cools down and then accelerate and then heats up slowly as you exit the shadow, and then you repeat half a circle later. And now if you follow the trajectory of gas like that, basically gas approaches the shadow, cools down, therefore accelerates azimuthally. And as it accelerates smoothly, now it arrives at the shadow edge, the shadow exit, and sees in front of it, again, slower moving gas, because that gas in the starlit region is pressure supported. Therefore, there's a differential azimuthal velocity between the gas in the shadow region and the gas in the hot region, in the illuminated region. And you can think of it as the gas kind of sees a soft wall ahead of it, kind of like a headwind. So this manifests as the gas must rebalance its azimuthal velocity, and this manifests as a pulse. And this pulse now, there's a constructive interference of these pulses from the two shadow edges, and this manifests as a spiral that travels radially through the disk. So basically, you have a bunch of radial linear sound waves that are launched almost at the shadow exit, which then coherent they constructively interfere to form a spiral. And these spirals are something that can only be modeled by dynamical models. You can't infer that from geometrical arguments and form. But the good news is that they have actually been looked at. So there have been some dynamical models that show with simple arguments like let's just take a disk and block some light along some azimuth. So as you can see on the top right, you can see the heating rate is blocked in two wedges on the left and right, shown in blue. And if you run this model now dynamically and allow the gas to heat and cool self-consistently, this whole thing manifests into a sort of an m=2 spiral mode. So you get two spirals symmetric about the disk center. And these spirals then could be observable in scattered light. Andrew has a question. Yeah. You just muted yourself, Andrew.
I just unmuted. Could you go back to the last slide with the temperature profiles? Yeah. So I know you're just describing now how you're doing the heating and cooling calculation, and so sorry if you're going to get to this, but so Xiaowan and I were actually talking about this at a meeting a couple days ago, but especially at 15 AU, it looks like right, the temperature drop is sharp, but then the rise is slow, which is a little surprising. I don't know if you can explain that.
I'll get to that. The
Okay.
basic reason is that it's not sharp. It's actually less sharp than you see on the 30 or 60 AU range. The gradient in terms of like D temperature over D phi is weaker. And the reason why there's weaker perturbation in general is because the disk is optically thicker on the inside. So there's a self-consistent radiative treatment that you'll see in my models that takes into account the optical depth of the disk as a function of radius as well. So you'll see stronger perturbations further out because the disk is optically thinner, cools faster. You see stronger temperature deviations further out, but it will come later.
Great. All right, thanks.
So as I was saying, if you set up a simple model where gas allow to heat and cool, and you block some heating along certain azimuths, then you recover these spirals. And then if you do some synthetic imaging of this in scattered light, for example, you can see that these spirals should, in principle, be observable. So these are some older models from almost a decade ago, actually, that show that it's possible to observe these, and you can even then sprinkle some dust particles in this kind of model and let the particles trace the gas in post-processing, so not as part of the simulation. And you would find that if you choose large particle sizes such that like Stokes equals 1-ish particles, such that they couple very strongly, they follow bumps in the gas structure very well, then you can see that these particles actually trace the spirals themselves, and you can even see the shadow lanes on the left and right here. So this looks promising on one hand, but on the other, we don't see anything at any additional substructures. We just see a few spirals, but that's it. So none of these crescents, these arcs that you saw before. So we thought, let's reinvestigate that, and let's do it a little bit more carefully this time. So I'm going to present to you some models that are vertically integrated, for one. That's the weak part, let's say, of this model, but it doesn't matter if we look at the midplane, because that's the area of interest. And we're going to have a radiative treatment that involves starlight heating, so the stellar radiation, the gas is allowed to cool vertically off through the disk surfaces, as well as diffuse heat through radiative diffusion along the disk plane. This is the first model in this series of papers on shadow disks that actually includes in-plane radiative diffusion along the plane in this 2D treatment. And on top of that, we're going to add the dust component live as part of the simulation evolution. So we're not going to add the dust as a post-processing component, but really the dust is actively evolving inside the simulation. And there's a two population model of dust here. There's small dust, which essentially does most of the cooling. There's also large grains, millimeter grains, which serve mostly as traces of substructure. So if there's any bump in the gas somewhere, these grains must follow it to some extent. But they also supply part of the cooling. So there's a nonlinear relationship between how much gas can accumulate dust, but also how efficiently the gas can cool by coupling to said dust. So the dust, both of these dust species have their own opacities. They contribute to the overall cooling, to the overall opacity of the gases. And we can then play with the free parameter of dust growth, sort of snapshot the dust growth process by essentially assigning an initial fraction of the mass between the large or the small grains. So we typically assume here a dust to gas ratio of 0.01 across both species, where 90% of that mass is in the large grains. So we expect to be looking at something along the class 2 phase of the disk, T-Tauri phase, where some significant dust growth has taken place. So we have 10 to the minus 3 of the mass dust to gas ratio in small grains, and the rest of the mass is in the millimeter grains. And this model now enables us to do the most self-consistent modeling of this interplay between gas and dust in these shadowed disks. And from that, we can now infer some synthetic observations of what should both the millimeter emission and maybe the some scatter light predictions would look like following our model. And I want to stress that because it's 2D and it doesn't go into the full 3D that the work by Shangja, for example, has gone, but without dust. Because it's 2D, we can essentially run these for very long time scales. So we can really probe nearly mega year long time scales, which is the first in this kind of work. So before we jump into the model, what we need to do first is prescribe a good model for the shadow. So we can, in principle, just plug in, just block some light along a certain azimuth, but we can do a little bit better. So we start by constructing a three-dimensional disk structure on the left. This is a simple Python model of two disks, with one of the two disks being misaligned by, let's say, 30 degrees. And now, having this set up, we can now ray trace from the center outwards to compute the optical depth that the disk sees from, with respect to the star at all azimuths, heights, and radii. And you can see on the top right here that if I take a slice of the heating rate that this could see, there's two very clear shadows on the top and bottom of this, and it looks almost like a step function, the depth of the shadow, which is a little bit unlike the other models that we've seen where you just plug some sort of Gaussian decay, which is quite a bit smoother. But we can now just take this, and if we look at any azimuth, we can plot this model, the heating rate, which you see basically plummets very close to phi over pi equals 0, and we can just model that with a sort of with a mask, where we can multiply now our heating rate that comes from a star along those azimuths with this mask, and now self-consistently recover what the heating rate should be, and almost self-consistently what it would be in the full 3D case. But we only do the 2D evolution here. And it's worth noting that because we don't capture the actual ray tracing during the simulation, this assumption that this mask remains static over time remains consistent, because the disk temperature structure doesn't change significantly. Therefore, the disk surfaces don't change significantly. Therefore, this mask remains the same as a function of time.
This is like a 90 degree or what's
This is 30 degrees.
30 degree, yeah.
But at the midplane, it only cuts off that that wedge. Of course, it's going to be an equal wedge on the other side. So this is only one part of the disk that you see here. But yeah, in principle, if I took the 3D results that I have here and looked at different heights, you would see that the two shadows sort of converge together, because it's a 30 degree misalignment, not a 90 degree misalignment. Cool. So we plug that into our simulations, we run the models, and lo and behold, you can see on the top right the temperature variations very quickly establish a 15-ish% temperature contrast between the shadow region and the illuminated region. The gas rotates as the arrow following the arrow, and you can see gas comes in hot, so there's no temperature perturbation. And then as you enter the shadow, you start cooling, and then you start heating up again. And you can see that the coldest parts are the ones further away from the star, and that's simply because there's a natural gradient of the cooling time scale as a function of radius. The outer disk is cooling much faster than the inner disk because it's optic thin. And you can see also on the left here, on the temperature perturbation profiles that I indicated before, that Andrew also pointed out, that the inner disk shows very weak modulations in the temperature deviations compared to the outer disk, which shows a 15% contrast between the shadowed and the illuminated region. And this, the byproduct of this temperature variation along azimuth is that we get these spirals that I mentioned before. So you can see on the bottom right, if we look at the perturbed density with respect to the initial quantities, there's a large m=2 spiral mode, but set of spiral modes that covers the whole disk. So if you take any point in this plot and follow it along a full circle, you will arrive, let's say, if you start from here, you reach here. This covers one full rotation of the spiral, and there's another spiral in between. So there's a large m=2 mode going through the disk. And I'm going to show you now in this animation here of how this evolves with time. So here I can actually use my cursor because this is a video. On the left, you're going to see the temperature perturbations. I'm going to just stop it here, which quickly established to about 15%. On the middle, you'll see the density perturbations with respect to the initial state. And on the right, you're going to see the brightness temperature computed by the combined emission from both small and large grains. Mostly what's going to be important is large grains, because you'll see they start accumulating at certain places. And that's what you see here. So this is what an observation would look like, in other words. And this has already been convolved by the beam size about the size of the cursor, just so you know. So it's going to be a little bit blurry, but you'll see things clearly. So if I let this evolve, please focus on the middle panel where you see these spirals. But now these spirals over time start merging into rings. So, and if I extend the color bar, you see that these rings just amplify in size, in amplitude rather, over time. I can play this animation one more time, if it allows me. So you see that we start with spirals, the spirals start merging into rings, and the rings just become brighter and brighter over time. And you can even start making them out in the brightness temperature on the right. So what we arrived at now is we started from a spiral-looking structure, but now we recover something much cooler. We start seeing a set of concentric rings in the gas that the dust particles slow down against, and therefore we start seeing this ring pattern on brightness temperature in millimeter emission. So this is what it would look like with us excluding telescope noise in a perfect observation in ALMA band 6 in principle. So ALMA, so 1.3 millimeter emission. So let's try to explain why this is happening. And I have this sketch here, which should hopefully explain the reason. So we can start by having a misaligned inner component. You see the yellow bit here. This misalignment here casts a set of two shadows, where you can see this blue lanes on either side in the temperature. Now gas arrives from the bottom right, enters a shadow, and cools very efficiently inside the shadow, and therefore accelerates. Now it hits the shadow edge, and this perturbs the gas, which for some reason causes the gas to deliver angular momentum locally in these locations. And this drives material away to the neighboring regions. And because we have a coherent spiral mode, this is done in an organized manner. So it's going to be radial locations of the disk that preferentially remove material, and the regions in between them accept this material. So there's no global radial motion in the disk. It's really an exchange locally between spiral modes that starts forming density perturbations. And of course, the dust happily will accumulate on these density perturbations. So we'll accumulate on the density peaks, and we'll start forming rings. And now, of course, this motion on the top right will now have to repeat as we enter the shadow on the left. And this process repeats and enhances itself in a feedback loop over time. Rather, it's not really a feedback loop, it's just a linear growth of contrast in the density in the gas, which starts building a contrast in the dust density. And then you start seeing these rings. And you'll essentially see rings spaced out by the radial spacing of the spiral modes. You can ask me more about this later. And I still need to explain how we go from spirals to rings. And I mentioned that there's for some reason the spirals deliver angular momentum in the disk. And this is really related to what I mentioned before, that the gas sees a headwind, it sees like a spongy shadow exit, and you can find that there's a radial correlation between the radial velocities of the gas, of the spiral that manifests, to the azimuthal variation of the variation of the azimuthal velocity as the gas exits the shadow, and this manifests as an angular momentum flux. You can see here this sort of arcane quantity that is defined as the correlations between the perturbed velocities. And if this quantity is positive, anywhere it's positive, you'll start seeing material be removed from these locations, and you can see it here on these purple points on the right that alternate radially. And in between them, there's going to be a negative angular momentum flux because it just receives the material from the regions where the spirals have removed angular momentum. Think of this as in a hand-wavy way, it's a very, very soft analog to spiral shocks, right? That maybe you see from a planet, that if you have a spiral that shocks, it removes angular momentum, it starts carving a gap. This is the same-ish process, but much, much softer, much more linear. But because this angular momentum flux is constant, as long as the shadow is there, the spirals always deliver angular momentum at a steady rate. That means there's a continuous gap opening on certain radii. And you can see here radial azimuthal averages, rather, so radial profiles of the perturbed quantities. On the bottom, you see the angular momentum flux again. You can see it's very constant with time. Different colors are different timestamps. And wherever you see a positive angular momentum flux, you can see a negative gas density undulation. So these grow with time. You can follow any of these colors. You can see it starts getting deeper and deeper with time. And if I really took a slice there and plotted this amplitude as a function of time, it's really a straight line as it grows. But you see that for a density perturbation of order 2% in the gas, there's a dust density perturbation of order 50%. So the dust really loves these bumps and just piles up on them. Andrew had a question.
Yeah. Thanks for letting me interrupt again. I'm just trying to understand why this angular momentum flux is varying in radius. I understand there's something happening as the gas goes through an azimuth, but
this is the exact same thing I'm going to
the wave structure and radius.
I'm going to cover this right now. This is the next.
Okay, sorry.
No problem. It helps segue things. So yeah, why is this happening? Why is it dependent with radius? You can see the inner part looks boring. There's not much going on. The outer part looks very structured, quite interesting. So there's a simple criterion to be made here that we simply, to see a strong spiral, we need the gas to have a significant velocity perturbation in azimuth between the shadow region and the illuminated region. In other words, we need the gas in the shadow to cool significantly compared to the illuminated gas. And so this puts a lower limit, an upper limit on the cooling time scale. So the important quantity maybe is not exactly the cooling time scale, but the ratio of the cooling time scale to the time it takes to cross a shadow. So the shadow crossing time scale, which is really a function of how wide the shadow is in azimuth, because in units of orbital periods, it's going to be constant in regardless of radius. So if we go work out this ratio of the cooling time scale of the gas, which is really depending on the local opacities, the local densities, local temperatures, to the time it takes to cross a shadow, we can work out a critical cooling time scale where these two equal. If the cooling time scale is longer than the shadow crossing time scale, then we don't expect to see significant features. Whereas if the cooling time scale is much faster than the time it takes to cross the shadow, then the gas cools very efficiently inside the shadow, and you should see a very strong angular momentum flux. And you can see on the right here, I've split the 1D plots on the right in half, and this vertical dashed line is really where this cooling criterion is met. On the left of it, it is not met. and on the right of it, it is met. And you can see this cleanly splits the disk into structured outer disk and then unstructured and rather boring inner disk. And even if you look at this on a 2D heat map on the bottom left, you see again, I'm marking the region where this criterion is met with a dashed line, and you can see the outer part shows rings, the inner part is quite white. So there's nothing going on there. And this is a very simple argument. It doesn't come from linear analysis or anything. It's a simple hand-wavy argument of I would need the gas to cool substantially in the shadow in order to produce a strong spiral, which then will produce a strong angular momentum flux, which then will produce rings. Andrew, I hope this answers your question.
Alex,
Yeah.
So Sanja and I have a pretty linear theory.
Yes.
To explain the spiral and the ring formation. So I think the angular momentum flux variation has two parts. The first part is if you only have a planet, right? The planet will excite angular momentum flux in a wave, but that angular flux has to be constant.
Yeah.
Because in adiabatic, this angular momentum flux of the wave is constant.
Yes.
So in order for it to vary, you have continuous excitation. So the first thing is the shadow has to be extended throughout the disk.
Yes.
If it's just the local temperature perturbation, you will have a local bump and then it will be flat.
Yes.
But the shadow is different from planet because it's throughout the disk. So you have this coupling between the shadow and the spiral density wave. That additional coupling give you the variation. The other one, the wide open gap, because in the purely adiabatic disk, you still have the angular momentum conservation. But because in the localized isothermal case, you do not conserve angular momentum, but conserve the angular momentum over CS squared. Yes. That quantity. So the angular momentum can be extracted between the wave and the background disk. So this is it's not a nonlinear effect, right? So normally the gap opening is you steep into shock and you open gap. So
the planet case.
So planet case is a nonlinear effect. But in these disk which cools very fast, then you have this angular momentum not constant even in the linear model. So in this case, you could extract angular momentum from a linear wave with background disk. So then you could open gaps. So
yes.
Even with very small density perturbation. So in this sense, it's a little bit different from the planet opening case. First is it has the coupling throughout the whole radii. The second is that the local cooling help you to extract angular momentum from the wave. Does not have to be short. So I think that there are these two a little bit different mechanisms.
Yeah, it's not exactly the same as a planet's process. You said that's a nonlinear process. This is simply a linear wave going through the disk, exactly what you just mentioned. And you need the shadow to cover the whole radial range, or rather, you only see rings manifest in the radial part of the shadow exists, because you need this spiral mode to exist there. Otherwise, it's not forcing exactly. And again, I want to point out these the azimuthal perturbations in the velocity are ordered like a few percent. They're not like Mach 1 with right background flow. So again, as you said, it's a different process, but hand wavily, it's really the correlated velocity between radial and azimuthal that just gives you an angular momentum flux, right?
Right. So it's very interesting phenomenon, right? Because this is a very small amplitude wave and can lead to gap opening.
Yeah, but because it keeps flowing over long times.
But you can extract the angular momentum from the wave.
Yeah.
And so the cooling is really important. If the cooling is too slow, then you won't be able to extract. Then you can.
Yeah. And actually, if you look at the previous models that I showed before, where they got the spirals going, they unfortunately didn't see the shadow, the rings, because they only ran for the equivalent of 10 orbits at the reference radius. So that's that's enough to see spirals. But if they had actually plotted something like an angular momentum flux, they would have seen this this thing here. They would have seen these purple and green alternating regions. And if they would have run longer, they would have seen exactly these rings. So fortunate for me, let's say that.
Yeah.
But still cool. Right, so we can make this simple.
Can I just ask you again? Yeah, no, so I appreciate a lot of these points about how this is not the standard case of angular momentum flux being conserved, and there's forcing over a broad range of radii, but then I'm not understanding where this radial wavelength is coming from.
Yeah, I can answer that. So I have a backup slide for this. So the radial wavelength is basically set by the radial spacing between a spiral that has just launched, and then how much radial distance can it cover before it loops back by 2 pi. So on the left, on the right, on top right, you see the density contrast for 3 simulations of 3 different temperature profiles. You can look at an aspect ratio as a proxy for it, and you can see that the dots mark the locations of peaks. And if I take now the radial difference, the radial spacing between these 2 peaks normalized to the radius of the inner peak, for example, you can plot the bottom panel, and you can see the dots follow a very regular spacing. Now, to explain the spacing again, all we need is to measure the distance radially that a linear spiral that travels at the sound speed can cover over a full orbit. And this makes it possible to just integrate this completely analytically. And you see it only depends on the bottom left formula. The spacing only depends on the aspect ratio. So really the sound speed, it's a purely kinematic effect. And from this, you can work out the plots, the curves in the dots on the bottom right, and you can see them match the simulation results very, very well. So it's really that the radial spacing between these rings is set by the radial speed of the spiral, so the sound speed really.
Yeah, the spacing basically is the spiral wavelength.
Yes, right.
Yeah,
Because the spiral,
yeah.
spiral wave now due to this coupling, they have very going up and down.
Mhm.
So the wave have this angular momentum pattern, but the total angular momentum between the wave and the disk has to be conserved. So that means the gap will be opened at corresponding peaks.
Yes.
Yeah. So,
but it takes the distance for the spiral to come back to get the next peak, and that distance is set by simply the sound speed. So a harder disk has less tightly wound spirals, and you can almost exactly model that with this very simple equation of just integrating a constant pitch angle. So this actually would make this observable. I'll get back to that later. That's not this plot I want to go to. You're running out of time. Okay. So that explains, hopefully, why this happens. Now we can start making some predictions of what it would look like. And I want to caution here, these are 2D simulations. So you're going to see both ALMA millimeter band 6 observations, as well as VLT sphere scattered light H-band observations. But the latter, the scattered light ones, are an extrapolation, because I would need to take the midplane structure, assume it's in hydrostatic equilibrium, so puff it up, ignore any possible warping that might happen, and just look at what the wedges blocked by the inner disk would look like on top of the substructures that the outer disk provides, assuming some small range will get trapped on these substructures. And, actually, yeah, let's get to that first. So this is what it would look like. On the bottom left, you see the equivalent ALMA 1.3 millimeter picture. So you can see these rings very clearly. And I want to point out that the green circle here marks the outer edge of my simulation domain. So the outer disk looks boring simply because it's not part of the simulation. It's just that I put this disk model that I have my simulation results back into a larger scale disk, which I can then run through RandomC, for example, and recover this picture. And it's very faint. I'm not sure if it's visible on the screen. It should be visible. But if you follow from this bottom left disk, if you look at its northernmost point and start going counterclockwise, so think of this as a clock. You start at 12 o'clock and move towards 11 and then 10 o'clock. The temperature, the brightness temperature seems to drop. So you might see a slightly weaker, fainter signal at 11 o'clock rather than 1 o'clock. And that's because that region is what's coming out of the shadow. So this is really the shadow region, and to the left of it is material exiting the shadow and coming back to the disk. And you can see that the gas and the dust are colder inside the shadow, and that's why they emit slightly more faintly. And the same thing you'll see on the bottom side, from 6 o'clock moving to 5 o'clock, that region is slightly fainter compared to, let's say, 7 o'clock. And you can do the same thing now for the scattered light observations. You can look at, let's say, different orientations, and you see these very bright the very bright disk surface, but with these two dark wedges that are not exactly 180 degrees apart because the inner part is tilted by 30 degrees, not 90 degrees. If it was a completely perpendicular inner component, you would see them 180 degrees apart, but this is just an effect of the inner disk being inclined with like a 30-degree angle. And you can even see both disk surfaces if you incline the disk just right. You can see that the shadow on the top side, on the bottom second from the right panel, you can see the shadow on the top side of the disk, the front side, but also on the back side of the disk.
So here you mean the near field observation cannot see the rings.
Yeah, the rings are not visible in near infrared. Yeah, because the dust that you're probing here is the micron dust, which only shows a 2% modulation compared to the background profile. But the millimeter dust has like a 70% contrast, so you can really see the rings there. Now, we can play this game by, as I mentioned before, the cooling timescale is the important quantity here, right? So I can play this game for different cooling timescales. Now, I want to keep these models sort of self-consistent instead of just plugging the cooling timescale in, because my models, in principle, don't allow a cooling timescale as an input. They do the full radiation live. So what I can do instead is rely on the fact that the cooling timescale scales with the disk aspect ratio very strongly. So in my case, it's about -3. That means that if I were to double the aspect ratio for whatever reason, or quadruple the temperature, in other words, then I would be, the cooling timescale would be a factor 8 shorter. So that's a big jump. And so you can see here 3 models with an aspect ratio of 5% at 30 AU. These models are flared, so it's not like I'm plugging an aspect ratio in. But at 30 AU, my aspect ratio is by default 5%, coming from a balance of heating and cooling. But I can just tune the stellar brightness in principle, arbitrarily, to make this aspect ratio 7% or even 10%. And what you see on this bottom panel is that as I increase the aspect ratio, these rings break into vortices. And you can, on the 7% aspect ratio case, you can see 1 vortex per ring in principle. So you get like, you can count about 7 vortices, I think, here. 1, 2, 3, 4, 5, 6, 7 vortices. And that's simply because of the fact that this process is a linear growing ring forming process. So the rings just keep getting brighter, the gaps keep getting darker. Over time, this contrast in density between the rings and the gaps becomes so steep that the gap edges actually go Rossby unstable. And so these vortices are the product of the Rossby instability on every single gap edge. And this axis here, in a way, the difference between the 5% case and the 7% case is time. Think about it like that. So if I waited long enough, even the 5% case would eventually break into vortices. I actually did, and it does break into vortices. But now, of course, the radial spacing between these vortices is set by the background temperature as well. So they're going to be a bit more spaced out for the 7% case. But if we go even further to a 10% aspect ratio case, for example, so this would correspond to like a very, very bright Herbig-looking star. This 5% case represents a T Tauri classical star here, for example. And on the right, you see that these vortices have already run their course. They've started devolving back into rings, so they dissolve over time because they're exposed to both cooling and dust-gas interactions. And so the vortices on the inside have cooled, have diffused back into rings. So these rings here are really the evolved vortices over time. But the outer vortex is the product of 3 vortices in 3 different radii exactly. They merge into one massive vortex and leave this void behind. And this vortex is much larger, so it's more long-lived, and it will just take some time until it eventually decays. But these simulations, I stopped them at about 0.16 megayears, so it's not awfully long, but it's long enough to see the evolution of what you expect. So if you take this x-axis as time, you can see that you start with the formation of spirals, then rings. These rings can become vortices, and over time, these vortices will start again merging or dissolving back into rings, and you can recover this kind of picture. So we can do the same thing now for the same thing I did for the default fiducial case, I can do for all the other aspect ratios. And you can see here on the left, maybe we can focus on the Alma pictures mostly. You can see that we can actually see those vortices if it's possible from, let's say, if we integrate long enough. You could see these vortices, but you can also see that on the brighter models, so aspect ratio 7 or 10%. Oh, this is wrong here. That's supposed to be 10%. That's supposed to be 7. Okay, the captions are wrong. But you can see on the bottom left panels that you can even see the shadow in the ALMA picture in the inner parts, and even in the middle left panel, if you squint, you might see the shadow on the top and bottom parts of this plot. It's very hard to see, but it's there. But it's much easier to see on the bottom panel because the brightness is just so much. There's so much more flux coming from there, so it's easy to see the contrast between the bright and the shadow regions, even by eye. But in the skylight pictures, again, you don't see so much. Maybe you start seeing some arcs in the for 7% aspect ratio. That's simply because we have significant amount of gas trapped in vortices, and now we're really just tracing these vortex structures because the micron grains just trace the gas. And on the bottom, you don't see the big vortex simply because it just happened to be in the shadow at the time that I was making the snapshot, like I was doing the ray tracing. So the vortex is sitting somewhere in the shadow here on the bottom row. That's why it's not visible. So one step further, since we have these very nice ALMA observations here, I thought I would go all the way to actually computing some synthetic images involving the telescope noise. So I run these results through CASA, which is a software that is designed to emulate the real noise coming from the telescope array in ALMA, and assuming some integration time, some weather conditions, and so on, and some distance to the source. And you can see that this is the fiducial model, and even with all these parameters considered, these structures are still observable. You can see on the left, you can still see the rings and the gaps. And remember that these will keep amplifying over time. So if I run this a little bit longer, so twice as much, that's still 0.3 megayears. The rings are very easy to see in this setup. And that's cool because there's, you can do the same thing for all of them. But that's cool because you can see all these features in D-sharp, right? But there is very cool new observation in Sigma Orionis by Jane Huang et al., which shows all these rings here. And I don't want to be provocative about it, that this has to be a shadow, but I do want to point out that this source is in a very high FUV environment. So there's a very bright nearby star that's casting light on this disk. And you can work out that, again, you expect this disk to self-shadow and start forming spirals and rings. There's an upcoming work that we have with some colleagues from Queen Mary on this. But it's consistent with this kind of picture. So shadows could be causing a ton of concentric rings in these observed systems. And another thing maybe I should point out here is that I know recently you guys have been working on a streaming instability code comparison as part of PFITS. And I was asked, I gave this talk a couple months ago, and I was asked, how would these be relevant to streaming instability? So if you plot the dust to gas ratio in these models, again, I don't capture streaming instability because these are 2D simulations and low resolution. But if you were to plot dust to gas ratio, you would see that on these vortices, you easily hit dust to gas ratios of 1 or even more than 1, 3 in this case. But even in the case of the fiducial model, after let's say 160 kiloyears, you already reach a dust to gas ratio of order 10%, and it will just keep growing as you run the simulation longer. So you're in a case where the streaming instability might start coming into play. You have a dust to gas ratio of 10%, a Stokes number of like 10 to minus 2. Maybe over time you can reach higher dust to gas ratios, start seeding a streaming instability, start forming planets. I don't know. So this is a hot topic at the moment. There's a lot more work on this, and so our models focus on the dust-gas interactions and how this would look in ALMA. But there's also a more general study of parametrized models with, let's say, varying alpha viscosity, varying the Coulomb timescale as a constant number, and you can work out whether you expect to see vortices or rings or spirals or whatever. But again, I want to point out that this is just really the time axis problem. So spirals will become rings, rings will become vortices over time. So all of these results can be actually compressed into a time evolution that these guys found here. There's also 3D simulations with full radiation transport, but no dust, but that's fine, because if you're interested in the skylight observations, you can see these very cool spirals here with the dark wedges on the top and bottom. that are very reminiscent of the system HD 142.527. And finally, as Jochen mentioned, there's also a linear theory on this that can all actually predict what the angular momentum flux at a given radius would be. So you can now integrate this in time and recover what the ring structure should look like as a function of time. And all these studies are very complementary in explaining this phenomenon. So it looks like we're developing quite quickly in this regard. So as a summary, just to reiterate, we start with a misaligned inner disk, which got there for whatever reason, maybe a flyby, for example. And then you have gas coming in hot, entering the shadow, cooling down. As it reaches the shadow edge, it bumps against the slower orbiting hot gas. This drives an angular momentum locally, which starts forming gaps. The gaps in between them start accumulating gas into rings, which the dust grains get trapped against and form very bright rings in continuum millimeter emission. And again, this process amplifies over time as the gas simply orbits around the shadow disk. And this can actually drive rings, even vortices, and both of these should be visible in both ALMA and maybe in H-band with scattered light observations. And this is quite cool because you can actually drive planet formation there. These could be sites of streaming instability as time goes on. Now, before I close here, I just wanted to advertise a little bit of other things I'm doing that might be of interest. So I know that you guys are working on this, so this is not news to you. But some of the people in the audience maybe have not seen this. So there's this streaming instability code comparison going on as part of PFITS. And a colleague of mine through this introduction is providing results with the code Pluto. This module is what I actually used for all of these simulations I showed. So these include whatever produced these streaming instability results is also what produced my results in 2D, which is quite nice. And now we're working on extending this module to be second order implicit in time to make sure it's stable and accurate. And some preliminary results look quite good. You can get this sweet error versus resolution curve that scales with resolution squared, which is quite nice. And you can apply this to multiple things. So I also have these simulations with the planet disk interaction and whether we can form bright substructures of the outer disk, and looking at how both the dust and gas back reaction as well as the opacity feedback between accumulating dust and now this dust affecting the cooling timescale affects the formation of substructures. And you can find, if you look at the right, that you can get interesting things that have not been seen before in simulations, where you get a ring as well as a vortex on the side of the ring instead of on top of the ring. So we have the two different topologies here, where the rings and the vortices can coexist simply because of this interplay between dust and gas interactions as well as thermal interactions between opacity accumulating where grains.
What's the 99% growth?
Assuming that 99% of the small grains have grown into big grains. So dust gas ratio of 10 to minus 2 in the big grains and 10 to minus 4 in the small grains. And other things I've been working on, I'm now working on the inner rim of planetary disks and looking at outbursts. So if you start with, if you haven't visited this model, you would see something along those lines, that disk just establishes an equilibrium state where gas is heated and cooling self-consistently such that no accretion is being driven. But if you try to model the MRI there and allow this hot gas to get ionized, then the viscosity changes locally. What you get is a burst. And this burst can start forming substructures, which could be the sites of planet formation in the future. So you see in this time evolution, as a burst that forms a bump on the outer side, and then the disk is cooling down, receding. And as it does, you will see an additional reburst here. And this process will repeat a few times. And then these bumps that are there could be sites of planet formation as they survive while they're being diffused viscously. And the last thing I could point out is I'm also working on planet migration, assuming planets have successfully formed. And we have these maps of different migration regimes as a function of the cooling timescale, which seem to be nicely reproducing observable populations at the moment, although we have just a few simulations to compare against. But I would just like to show one simulation here that looks quite pretty. If you look at this time evolution of the gap structure on the planet, you see all these little vortices forming around it, which are a combination of Rossby instability as well as baroclinic forcing due to cooling and how cooling interacts with these vortices. And this has a very profound effect on planet migration. But I found that it would be nice to show it because there are some people here that have worked in the Rothman simulator quite a bit, and it might be interesting. And you can see that a gap starts being carved very efficiently because of this inclusion of cooling, and results in the planet completely stalling. And if you were to compare it against a model without cooling, on the left, the blue curve shows the planet drifting inwards, but on the orange line that includes cooling shows the planet completely stalling. And I'm going to leave it here and maybe put up my summary slide. And thank you for your attention.
Vlad, I'll turn it back over to you to close up.
All right. Thank you. I suppose that you make the call for questions?
Yeah, I mean, I know we hit the hour here, and if anyone needs to go, no worries. I did provide Alex's contact information in the announcement email I sent out, but if somehow you need to get in contact with him and you can't find that, feel free to contact me. But if anyone wants to stay for a couple minutes here for questions, feel free to do so, and go ahead, ask away.
All right. All right, folks. So yeah, if anybody wants to, needs to leave, yeah, please feel free to, but if you want to stay for questions.
Go ahead, Arthur.
Here.
Yeah. So for your rings to form, and then you show that if you go for a longer time, they start to form different structures. But you need your misalignment to have your shadows. You need it to be sort of permanent, right?
Yeah.
So if you have a more dynamic, you would only reach like the ring face, and then it would like disappear. If the shadow goes away, then this should disappear, right?
Yeah, it's a combination of the efficiency of cooling and how long you can force a distance. So if the shadow disappears after, let's say, 1,000 local orbits, for whatever it is, at whatever distance, then if at that distance cooling is inefficient, you might see nothing. If it's efficient enough, you might see spirals. If it's really efficient, you can already break into vortices within like 30 local orbits. So it depends on the balance between how long you integrate, or effectively how long the shadow lasts, how efficient the cooling is, and how wide the shadow is. So what's the ratio of the cooling timescale to the shadow crossing timescale, right? So it's a mix of these three, and this can be nicely arranged as a time evolution principle. But you're right. So there are some simulations, flybys, for example, that can cause misalignments to bend and break, and these broken parts can survive for, I think, like thousands of years, which is not that many orbits on the outside, but it might be enough to start seeing some substructure. And then if these substructures don't dissolve because there's no turbulence, or it's too weak, then you might look at a system, see rings, but then look at a scattered light and see nothing because the shadow is already gone by then, right? So it really depends on how long the shadow lives and if you get to see it. Yep.
And in that realm, if the inner disk is tilted and it's surviving for a long time, will it maybe processing? So can you have this,
Shadows moving,
adjusting as
Right. So that's a good question. Actually, it's a very good point, because here we assume that the inner part is not processing, and that's big. It really depends on what causes the inner disk to break and misalign. So if you have a companion inside the disk system, like a binary, you can very easily form a broken misalignment, which will precess as a function of the binary's parameters. But from the perspective of gas in the outside disk, it will see a rapidly rotating like coin on the inside. So on average, you won't see that strong effect. But there's always going to be some part of the disk where the local orbit is resonates with the precession timescale of the inner disk. And what happens then is that you can always find some gas that's always in the shadow, right? Because it's rotating at the same rate that the shadow is rotating. What happens then is you actually get, similar to what Javan mentioned before, you get a very local shadowing, which drives spirals locally, but these spirals are not being forced again at different radii. They're only forced at one point. And this looks a lot like planet-formed spirals, actually, to an extent. The pitch angles are different, but but they look like those. So this would mean that the ring formation is less efficient over the whole radial scale, but it's really efficient there at that point that you resonate with the shadow.
You might get like one ring, one sharp.
I get one ring exactly, yeah.
At the co-rotating.
For example,
area,
yeah. So
yeah.
that's something that hasn't been looked at yet, but I was thinking of doing it soon because in principle I have a setup, I can just like run it. But that's my prediction because based on all these like arguments about angular momentum flux and the spiral driving and so on, the logical explanation to me is that you should see gaps where you force the gas, and you only force the gas at co-rotation with the shadow. Yep.
So one more. So as a summary, it's like a fundamental unified explanation. You could say that for your bigger stars, which are much hotter, this process is much faster as you show that you have a higher aspect ratio. So your rings collapse into these vortices quicker. Therefore, you would have, we're saying that in vortices, you reach a parameter form planets.
Right.
That could form planets. So planet formation occurs faster in hotter disk with higher.
We need to be really a little bit careful interpreting the statement because here I'm a theorist, so I can play with the parameters however I want, and I chose the aspect ratio as my reference. But really, the aspect ratio is a measure of the cooling time scale. Everything else kept the same. So a hotter star, like a more massive star rather, like a Herbig, will likely have a more massive disk around it, right? And sure, the aspect ratio might be slightly higher, although comparable. The cooling time scale, though, might not scale the same way because a more dense disk cools less efficiently. So it's a whole nonlinear process. My statement would be that disks around stars that have disks with a very fast cooling time scale, whatever that causes it, be it an optically thin gas or really high, really low, or really high opacities in the optically thin regime, or anything that, as long as your cooling time scale is fast compared to the shadow crossing time scale, that's the condition to see fast formation of rings and then vortices. It just might be that there might be a small bias towards the more massive stars, but I also want to point out that we have, of these 12 sources that I mentioned before, that we see shadows, they're half and half. So we see shadows in both Herbigs and T Tauris. It doesn't seem there's a clear preference for shadows, but we don't know if there's a clear preference for substructures. Not all of these have been looked at one wavelength, have been looked at the other.
Any questions from online? Cha-Chen, go ahead, please.
How did you implement dust cooling? Is it a small dust or large dust that's efficient?
So I dropped that slide. So it's a two population dust model where the small grains are tracing the gas and the large grains are freely moving around. And each of them has its own opacity model that is temperature dependent. For the large grains, it's mostly flat. But then what I can do is I look at a particular location in the disk. I can see how much small dust I have, how much large dust I have, and I can combine these two to an overall opacity that is then fed into the radiation function, the radiation module in the code that does the cooling on the gas. So this makes the implicit assumption that the gas and the dust have the same temperature and they are perfectly coupled thermally. So dust grains and gas are collisionally coupled on very short time scales such that they can actually do this. So the dust itself doesn't have its own temperature, just follows the gas. Now, in terms of the opacity that dominates, if your dust grains have grown by 90% from the small grains to the large grains, you can actually show that the opacity contributions at these temperatures, so like at 30 Kelvin or so, between large grains and small grains are actually comparable. And that's because the small grains have a factor 10 higher opacity than the large grains. That makes sense. But you have 10 times more big grains than you have small grains. So if you do the density weighted average of opacities from big and small grains, they contribute roughly the same amount. And from that, you can work out that you can actually get some feedback effects where if you trap a lot of big grains, you start making these areas a bit thicker. which makes them harder to cool, and this whole thing wraps into itself. But I can tell you that I ran some models where I don't include these effects, and I get the exact same results. These results are very robust because they only rely on cooling the gas. It doesn't matter what the dust is doing. You can recover this with just gas and the simple cooling parameter.
How about vertical effect?
Sorry?
How about the vertical distribution?
Vertical effects, right. So in my models, the vertical effects are absorbed into a vertical emission. So assuming that the midplane cools over some time scale vertically upwards with some effective optical depth, but it doesn't actually capture the diffusion live because it's a 2D model. But the model itself, even in 2D, it's quite good, I would say, in capturing the temperature evolution at the midplane. I have some 3D simulations in a different context that show identical results. As long as you do the cooling right in 2D, you can get very similar results to 3D models in terms of the temperature evolution at the midplane. Now, if you had a misaligned inner disk with some angle, like 30 degrees, you would start seeing warps. You would start seeing something like this. That one side is hot, one side is cold uniformly. And this would start giving you some vertical motions. This I can't model in my simulations, but there is upcoming work from Zhang that is looking exactly at that with gas-only simulations.
Since the effect is most important when optical thin, right? So the vertical diffusion is not.
Well, not as much, yeah. Because you would need to actually propagate that temperature deviation down to the midplane to see anything.
Alex, I do have a question. You said that in the previous slide that you were showing that you are also considering dust growth, but they're saying there are snapshots of dust growth. So what exactly do you mean by that? Is the dust growth like through coagulation and fragmentation done at the same time as the hydro, or?
There's no dust growth during the hydro phase. What I can do is, because I have a two population model, I can, at time equals 0, split the mass reservoir in small and big grains. And assuming some dust growth has taken place already, I can split it. Let's say I can put 90% of dust in the small grains, which will be my class 0, class 1 phase, or I can put 10% of the dust mass in the small grains and 90% in the big grains, which will be my class 2 phase, or put 1% the small grains and 99% the big grains, which would be like late class 2 phase. All this does really is it essentially affects the cooling timescale as well as the brightness of the features you see, because if you have more big dust, you see slightly brighter features. And you can see on the right here, on the rightmost panel, the number you see here is the fraction of mass in large grains. So that's the dust growth factor. So on the top left of that panel, the blurry image is a model where 90% of the dust mass is in the small grains. So this disk is more thick. There's less big grains. So you see more diffuse structure, fainter, and it's harder to cool. So you see less substructure as well because you don't meet the cooling criteria I mentioned before. But as you grow the dust more and more, you see more crisp features. There's not that much difference between 90 and 99% growth, but it's a very stark contrast to the early phase. So it's really like it's a free parameter of how much big grains do I have access to. Just plug in at time 0.
But so it's not just post-processing, it does affect the hydro.
It does affect the hydro, yes. All of this is done live, yeah, but the dust species are not allowed to trade mass between them during the hydro phase.
Right.
There's no coagulation or growth or anything, yeah, not even a two-pulp model, because we wanted to really just isolate these two and focus on the cooling effects, yeah.
And the left is that alpha?
Yeah, the left is a different alpha.
Force turbulence, or is that when you put viscosity?
Viscosity,
Yeah.
And a minor curiosity, you said that the spiral arms that are launched are M-equal 2. And you likened that to the planets, but planets launch M-equal 1 spirals. Is there a reason? I mean, is there an obvious reason why this process launches M-equal 2?
Yeah, it's an M equals n, where n is the number of shadows. That's all. So in my case, I have 2 shadows, so you get 2 spirals.
No, all right, yeah, that makes sense.
But if you had 2 corrotating shadows, like a rotating shadow, then you will get a set of of spirals, like an inner and outer spiral per shadow. So a total of 4 spirals.
Okay.
Or 2n, where n is the number of shadows.
Right.
Any more questions? If not, let's thank Alex again. And thanks everyone for this first joint meeting. Thanks, Andrew. And stop the recording.
Or to stop.
No, I have to.